So, hello students, welcome to EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about symmetries in molecules and crystals part 2. We will continue with what we learned in the previous module. All this is from the paper Mathematical Physics. So, let us see what we are going to learn in this module. In this module, we will learn techniques to identify various point groups associated with the underlying symmetry of the molecule. We'll give you some techniques on the basis of which you can easily find out all the underlying symmetry operations of the molecules rather than looking at the molecule and looking at all the possible symmetries. We'll give some tips, but using that you can easily identify the symmetry of the molecule. Let's first talk of molecular point groups. A molecule, as we have seen earlier, can possess any of the 32 crystallographic point groups. In addition, they may be invariant under other symmetric operations which are unavailable to crystals. For example, a molecule may be symmetric under a 5-fold or 7-fold symmetry which is not available to a crystal. As I said, there are some molecules may possess 5-fold rotational symmetry. The HCl molecule, for example, the other molecules, the HCl is chain molecule which possesses full rotational symmetry. That is, it is invariant under a continuous rotational symmetry about the molecular axis. It has no other symmetry. Its point group is simply C infinity. That along the axis of the molecule, you can rotate it by any angle and the molecules appears to be the same. So its point group is C infinity. Then you have linear molecules like carbon dioxide, CO2, which may have full rotational symmetry about the molecular axis. So it has full rotational symmetry along the bond axis. So you have CO2, so it has full rotational symmetry along the bond axis, and in addition, it has 2-fold rotational symmetry written as C2 prime about any horizontal axis passing through the center of the molecule. Moreover, or in addition, there is also a horizontal mirror plane sigma h. So for a molecule like this, CO2, the point group of symmetry is D infinity H, which is equal to C infinity plus there is an infinite number of 2-fold rotations and there is a mirror plane symmetry in the horizontal plane sigma h. Now we will discuss the identification of molecular point groups. How do we identify the point groups of a molecule? In order to identify a molecular point group, we need to identify all its symmetry elements, which is a cumbersome process. In practice, however, there are simple ways to obtain the point groups by following some methods which I will discuss in detail and are outlined subsequently. To start, we find out if the molecule belongs to a special group with the aid of the following observations. What are these observations? We will see. Number 1. If the molecule is linear, its symmetry group is either CAV or DAH, depending upon whether the molecule possesses a 2-fold rotational symmetry about the horizontal axis passing through the center of the molecule, in addition to the full rotational symmetry along the molecular axis. So first thing to identify the molecule is linear or not. So if the molecule is linear, symmetry group is either CV or DH. So it has a twofold rotational symmetry about the horizontal axis passing through the center of molecules, in addition to the full rotational symmetry along the molecular axis. B. If the molecule has no axis of rotational symmetry, that is, there is no axis about which you can rotate the molecule by any angle, and the molecule does not come back to its previous shape, then it is a very low symmetry molecule whose point group is either a C1, C2. Depending on whether the molecule has no symmetry, one mirror plane symmetry sigma, or inversion symmetry respectively. So its group could be C1, C2 or Ci, inversion symmetry, or either C1 or C2. Number C. If the molecule has a higher order symmetry axis, so there is an axis which is called the principal axis about which you can rotate the molecule by an angle 2 pi by n. That is, the molecule has a higher order symmetry axis Cn. Then there are two possibilities. Either this higher order axis is unique, there is no other axis about which you can rotate, or there are multiple higher order axes. So in case you have only one Cn, one axis called the principal axis, which has n-fold symmetry, then the molecular, the point group to which this molecule belongs to could be either Cn or CNV or CNH, depending on whether in addition to this axis of n-fold symmetry, there is also a mirror symmetry in the horizontal plane or in the vertical plane containing the principal axis. I will now describe how to identify molecular point groups. We have seen all the symmetries which are possible in the molecular point groups, but given a particular molecule, how to identify to which point group it belongs is sometimes can be done easily by noticing a few important features. For example, if the molecule has a unique higher order axis, that is, at the principal axis, a rotation by an angle 2 pi by n is a symmetry of this molecule, and if there are no twofold axis of rotation symmetry perpendicular to this principal axis of rotation, then it can belong only to the point groups Cn, Cnv or Cnh, depending on whether it has a mirror plane symmetry in a plane which contains the principal axis, that is a mirror plane sigma v, which passes through the principal axis, or if there is a mirror symmetry about a horizontal plane which is perpendicular to the Cn axis. So it's very easy to then identify the molecular point group of a given molecule. So in short, if we have one axis of rotational symmetry which is n-fold, that is one Cn axis of symmetry, there are no twofold axis of rotation symmetry perpendicular to this principal axis. That is, there is no axis in the horizontal plane which will take the molecule back to itself if you rotate it by an angle pi. Then the point group it can belong to can be either Cn or Cnv or Cnh. Therefore, molecule has one principal axis of n-fold rotation symmetry Cn, no C2s perpendicular to the Cn. If they are further no reflection planes, then the group is simply Cn. If there is a reflection plane which contains the principal axis, that is the reflection plane sigma v, and such planes, then the group it belongs to is CNV. If there is a horizontal plane which is perpendicular to the axis, principal axis, then the molecular point group is CNH. Now, if over and above this principal CN axis, the molecule also possesses an twofold rotation axis perpendicular to this principal axis, then the molecular point groups or the molecule can belong to the point group DN, DND or DNH, depending upon whether the molecule has no mirror symmetry, in which case the group is DN. If it has n dihedral mirror planes, that is n planes which contain the principal axis but they lie along the bisector formed by three molecules, three atoms in the molecule, then the group is DND. Or if the molecule possesses a horizontal plane symmetry, plane mirror symmetry, then the group is DND. Thus, to summarize, if there is one n-fold axis of symmetry, which is the main axis, and in addition, if there exists n twofold axis of symmetry, which are perpendicular to this main principal axis. So, having first categorized this, then further, if there are no mirror symmetries, there are no sigmas, then the group, the point group this molecule belongs to is DN. If there is a horizontal symmetry, horizontal mirror symmetry, then the molecule belongs to the group DNH. If there are dihedral plane symmetries, then the molecule belongs to the point group DND. Finally, if the molecule possesses multiple higher order axes, so far we have considered only those molecules which have one main axis, one higher order axis, n-fold axis. Then, if the molecule possesses more than one higher order axis, its symmetry point group is one of the 5 special cubic groups. It could be O, OH, T, TD, or TH. All these groups have 4 threefold axes of rotational symmetry. The molecules with the point group O and OH are those which, in addition to the threefold axis of symmetry, also possess fourfold multiple axes of rotational symmetry and inversion symmetry respectively. In the absence of the existence of fourfold symmetry, then the cubic molecular point group is the group T. So if there is no fourfold symmetry, if there is a fourfold symmetry, then the group could be either O or OH. If there is no fourfold symmetry, then it belongs to tetrahedral groups, which could be T, TD or TH. So if the molecule possesses improper rotation symmetry, but no fourfold symmetry, the group is TD or TH if there is inversion symmetry. So to summarize then, if we find a molecule which has 4 threefold axis of rotation. So first thing is to see if the molecule has a threefold axis of rotation. So if we find that the molecule has threefold axis of rotation and they are 4 in number, then we go further and we see if there are any fourfold axis of symmetry or not. If there are fourfold axis of symmetry, then the point group to which this molecule belongs to can be either the cubic group O or OH, depending whether it has inverse symmetry or not. In case there is no C4 symmetry. There is no fourfold axis of symmetry, but only twofold axis of symmetry. In which case, to see how many axes of symmetry it has. If it has three twofold axes of symmetry, then this molecule belongs to the point group tetrahedral. It could be T group or TD or TS. The group T, if there is no improper rotation symmetry, though there is no inversion symmetry. If there is an improper rotational symmetry, it belongs to the group TD. And if there is an inversion symmetry along with a 3C2 axis and a 4C3 axis, then the molecule belongs to the group TH. So we can now make a summary of what we have learned. So there are 32 crystallographic point groups in 3 dimensions. And let me mention at this stage that in 2 dimensions there are 5 crystallographic point groups. So we have 32 crystallographic point groups, which we have shown in the slides. And I will explain the group name, the order of the group, and the essential symmetry elements of these 32 point groups. The first group name is CH. The order of the group is 2. It has only one symmetry. This is the mirror symmetry sigma. Then I have one inversion symmetry I, which belongs to the groups S2. The order of the group is 2. If we have one n-fold rotational axis, then the symmetry group is Cn and the order of the group is n. If we have one n-fold rotation axis plus n mirrors containing the principal axis, that n sigma v's, then the group is designated as CNV. It has 2n elements. If we have an n-fold rotational axis plus a horizontal mirror symmetry, then the group is CNH, which is a direct product of the group Cn with C1H. The order of this group is 2n, and the group is designated as CNH. Dn is the group whose order is 2n, and it has one n-fold rotation plus n two-fold perpendicular axis. And the group D1 is in fact identical to the group C2. The group DND has the symmetry operations, which are the Dn plus a sigma D. So the number of elements of the group DND are 4n, and D1D in fact is equal to C2H, and D3D is obtained by the direct product of the group D3 with the group ST. And the group DNH has 4n elements. The order of the group is 4n, whereas D1H in fact is just equal to C2V. And DNH group has the following symmetry. It has the symmetry Dn plus the symmetry in the dihedral plane, sigma D. So DNH is the direct product of the group Dn with S2 for n is equal to 2, 4, 6, or DNH is equal to Dn with the direct product with the group E sigma H for n is equal to 3 and 5. Then we have the group designated as Sn for n is equal to even. Its number of elements is n, or its order is n. And the group S1 is nothing but C1H. So it's not a new group. And this group Sn consists of one improper rotation. S3 in fact is equal to C3H. So group Sn has one improper rotation, but the group S1 is nothing but C1H, and group S3 is nothing but C3H. Then we have the cubic group, which has O, the cubic group O. Order of the group is 24. The group has 9 C4 axes. That is 3C4, 3C4 square, and 3C4 cube. Rotation of pi by 2, pi, and 3 by 2 about x, y, and z axes respectively. In addition, it has 6 C2 axes along the line joining centers of opposite edges, as we have discussed earlier. It further has 4 threefold axes along the 4 cube diagonals and 4 C3 square the rotation by 120 degrees and 240 degrees about the cube diagonals. Number of elements 24. The group OH consists of 28 elements and is obtained the direct product of the group O with inversion. So if the group molecule belongs to the group O with the further symmetry of inversion, then the group is OH. Tetrahedral group T has 12 elements. It has 3 C4 square, 4 C3 and 4 C3 square rotation. That is, it has 3 four-fold rotations, 4 three-fold rotations, and so on. The group TD has 24 elements, is a group of 12 proper rotations of T plus 12 improper rotations, and consists of like 4C3 square, 4C3, 4C3, 4C3 square, 3IC4, 3IC4, 6IC, etc. And finally, the group TH has 24 elements, and TH group is the direct product of T with the inversion group. Let us now discuss a couple of examples to see how to identify the symmetry, point symmetry of a molecule. Let's consider the molecule NH3. So on the basis of identification of symmetry elements and their point groups discussed above, we will use this example of the molecule NH3 to identify its symmetric elements. This molecule NH3 has a threefold rotation symmetry about an axis passing through the atom N. So you have N atom, there is an axis, so you rotate by an angle 2 pi by 3, and you can easily see that the molecule has this symmetry. So this molecule has a threefold rotational symmetry about an axis passing through the atom N. It has no other rotational symmetry. However, there are 3 sigma V mirror planes which contain the axis of rotation. Hence, its point group is C3V. So the point group of this molecule NH3 is C3V, and remember that the C3V is a group which consists of 6 elements, the identity, 2 rotations, threefold rotations, axis, and 3 mirror planes which contain the axis of rotation. So the point group is simply, in this case, C3V. Another example we consider is an example of a square planar molecule like XeF4. You can immediately see that this molecule has a 4-fold axis of rotation. 4-fold means rotation by an angle pi by 2 along the axis passing through the atom Xe. In addition, there are 4 two-fold axes, that is rotation by pi. 2 of these axes are along the line joining the opposite FF atoms, and 2 bisecting these bonds. So all the 4 two-fold axes are perpendicular to the main C4 axis. But these are not the only symmetry operations. In addition, there is a mirror plane sigma h. The horizontal plane, if you reflect about that, the molecule, it has the symmetry. Molecule has the symmetry. So the point group of this molecule is in fact D4H, and D4H has 16 symmetry elements comprising of the identity, 2 C4 rotations, 1 C2 rotation, 2 C2 double prime rotation, another two-fold rotation. Then I have the inversion, 2 improper rotation, sigma H, 2 sigma V's, and 2 sigma D's. So there are 16 symmetry elements of this molecule. Now I will give an example. I will see how to classify the symmetry group of the molecule. So let us consider the molecule CH4 or SiCl4. So this molecule has a carbon atom and with 4 hydrogen atoms bonded to it, or a silicon with 4 chlorine atoms. This is an example which is relevant for molecules belonging to the cubic symmetry group. This molecule has threefold axis of symmetry, and in fact there are 4 threefold axis of symmetry which lie along the line bisecting the each bond. So you have 4 threefold axis of symmetry, G4C3. Then you have 3 twofold axis of symmetry along the axis which bisects the pair of bonds. So these are 3C2. Then there are 3 S4 axis coincident with the twofold rotations. In addition, we have the mirror symmetry, which consists of 6 mirror planes sigma d containing the carbon atom and line bisecting the angle between HC and H. So there are 6 such mirror planes. The point group is therefore the group TD comprising 24 elements, the 24 elements being the identity, 8 threefold rotations, 3 twofold rotations, 6 improper rotations, and 6 mirror symmetries along the plane sigma d. Yet another example we consider is the example of the molecule cyclopropane. So you have a regular triangle consists of similar atoms, and there are 2 hydrogen atoms bonded to each of these atoms. So this molecule has threefold rotation along the axis passing through the center of the triangle as shown in the slide. So you take the triangle on which these 3 atoms, the 3 atoms belong to, and if you take the center of the triangle, then there are threefold rotation along the axis passing through the center of the triangle. So C3 symmetry operation. Then there are 3 twofold axis of rotation along the side of the triangle. So 3C2. Then there is a mirror plane sigma h in the plane of the triangle. So in the plane of the triangle, obviously there is symmetry. Moreover, 3 more symmetry planes with 3 more mirror planes sigma v as shown in the slide. And finally, there are 2 threefold improper rotations. So there are 12 symmetry elements comprising of E, 2, C3, that 2 threefold axis of symmetry, 3 twofold axis of symmetry, 1 horizontal plane symmetry, 2 improper axis of threefold symmetry, and 3 mirror plane symmetry sigma v. So the group consists of 12 elements and is the group D3H. Finally, let me give you an example of a point symmetry group, which is a cubic group. So consider a molecule SF6, which is a regular octahedral. Now, if you look at the group, this molecule has 3 fourfold axis of 3 fourfold rotational axis along SFS. So if you take SFS, they have 1, 2, 3, 4. The 4 axis is rotated by an angle. There are 3 C4s, fourfold rotation about FSF axis and 4 3-fold rotations. So this group has multiple rotation axes of symmetry. Is a 3 C4 axis and 4 C3 axis. So this molecule belongs to the cubic group, either O or OH. But in this case, the molecule also has a inversion symmetry about the atom S. Therefore, it has 6 C2 axis, a reflection plane S4 and S6 axis, and the symmetry group of this is OH. So let us summarize what we have learned in this module. The point group symmetries of all the 14 three-dimensional Bravais lattices are given in the slide, and they summarize all the possible symmetries. Thank you.